So welcome back to Network Information Hiding. Today I will cover Chapter 7. Chapter 7 is a bit longer and for this reason divided into two sub-chapters, 7a and 7b. This chapter deals with network level countermeasures. I already spoke about fundamental countermeasures in an earlier chapter that are not network specific, but now we switch to network specific countermeasures where I first talk about basic and then about sophisticated network level countermeasures that can also disrupt things like the null phase. So there are countermeasures and detection methods especially, right? Yes, there are. We can detect covert channels quite well, but there is not a detection method known for every type of covert channel and every pattern. So there's lots of research to be done, and the methods that we have don't always scale. So let's say you have to scan 10 gigabits link that is fully exhausted in the sense that the whole network capacity is used, and you have to scan this traffic in real time. And let's assume that you have a certain number of false positives. Let's say it's just 5%. Then if you have to analyze these 5% by hand and you have so many flows to detect that 5% are in the end thousands a day, then that's already infeasible and the countermeasure is not good enough. So we also need better countermeasures, at least partially. I will discuss details and limitations of some countermeasures later. For limitations, I will especially cover my own countermeasures to show you their limitations. But first of all, I will introduce some methods by other authors. In general, we can do three things. Either we can try to prevent or eliminate a covert channel, be it in the system design phase using the shared resource matrix methodology, or be it during the operating phase of the network or system. Secondly, we can limit the channel capacity of such channel. And thirdly, we can try to detect it at least. So in our book Information Hiding in Communication Networks, Chapter 8, we cover lots of hiding of countermeasures. I cannot go through all of these, and some of the methods that I show here are also not discussed in the book, but I will cover the basic ones that I think you really should know, especially the traffic normalization, which is a method to eliminate covert channels. Then I will explain 3 detection methods for the interpacket times pattern. And then I will show you 2 methods that combat sophisticated hiding methods, like the protocol channel aware active warden that combats protocol switching covert channels, and the dynamic warden that is especially tailored to limit the null phase. What is a traffic normalizer? Traffic normalization is also known as packet scrubbing. It's usually part of firewall or network intrusion prevention systems like Snort or the OpenBSD PF that also has a scrubbing feature. And in our terminology, it's a form of an active warden because it actively modifies the traffic and influences the covert communication if it is present. A core idea is the traffic normalizer is like a gateway, and the traffic arrives at it at one end, and the normalizer normalizes the traffic in a sense that some attributes are just modified in the traffic. For instance, reserved bits, if they are set in the IP4 version 4 header, then they could be cleared. Or inter-arrival times could be unified by caching and then delaying packets. So that's how it can work, and it's usually rule-based. So you have to write down rules for the warden so that the warden or traffic normalizer knows how to react to these to packets and how to modify the packets. Here you see the general components. So the normalizer has some buffer where the incoming packets and there are cached. Then there are the rules, and it also needs to keep state of flows. And then it tries to modify based on all the information that it caches and knows. It tries to modify the traffic accordingly. So for instance, the storage channel here contains 2 1 bits and 1 0 bit. So let's say that's the reserved bit and both 1 bits should be cleared, then the output could be 0 0 0, while the timing channel with different packet gaps here, different interpacket gaps, could also be normalized by caching the packets and then unifying the output, or at least making the output rather large so that the covert channel is at least limited in its functionality. The problem is that there are many fields to normalize, many fields to look at. Here's just a short overview. I took this table from chapter 8 of our book, and you can find the details there, but the problem is there are many rules that need to be programmed, and several of them, as you can see at the right side of the table, have side effects. So if you, for instance, overwrite some bits, then they cannot be used anymore. There are also certain other problems with traffic normalizers. There's an excellent paper by Handley et al., published already 2001, but it's so good I still cite it, and I cited it a lot in my own publications. They asked the question of how to handle overlapping TCP segments, such as those caused by retransmissions, especially if their payload differs. They gave this example. So we have sequence number 1, a packet arrives with TTL10, and the payload is an N. And then we again get a packet with sequence number 1, TTL12, payload is a yes, a Y, and so forth. And in the end, we need to figure out what kind of information should will arrive at the system and how will it be interpreted. So let's say the TTL is 12 or the necessary TTL is 12, then it could be no, but it could also become yes or yo or something else. And so let's assume in one variant, the payload in the end would be a malware, and in the other case, it wouldn't. So the normalizer usually doesn't know which segments will reach the receiver and what the potential consequences of all the payload combinations could be. So it would need to cache all the data and evaluate all possible consequences. But that's very time consuming and could, in the end, actually lead to an attack against the normalizer, because you just exploit its cache and let the cache grow and grow and grow and grow, so the normalizer becomes more and more exhausted, and in the end it might cause a denial of service attack. Another problem is that the design of a traffic normalizer can prove vulnerable to incorrect analysis during a cold start. That is, when the analyzer first begins to run, it's first confronted with traffic from already established connections for which the analyzer lacks knowledge of the connection characteristics negotiated when the connections were established, because it wasn't operating back at that time. So there are already existing connections now going over through the normalizer. For example, the TCP scrubber requires a connection to go through the normal startup handshake. However, if a valid connection is in progress and the scrubber restarts or otherwise loses state, then it will terminate any connections in progress at the time of the cold start, since to its analysis, the traffic exchange appears to violate the protocol semantics. And so an attacker could, or the warden itself could become, could have a negative impact on the legitimate traffic in the network. And then there's the state-holding problem. I already mentioned this briefly, just not using the word state-holding. So a network intrusion detection system, again, citation from the paper by Handley et al., must hold state in order to understand the context of incoming information. One form of an attack against the NITs is a state-holding attack, whereby the attacker creates traffic that will cause the NITs to instantiate state. If this state exceeds the NIT's ability to cope, the attacker may well be able to launch an attack that passes undetected. And further in the text, an attacker can thus cause the normalizer to use up memory by sending any fragments of packets without ever sending enough to complete a packet. That's what I meant here 2 slides ago. So we can send many packets with sequence number 3, for instance, and then this needs to be cached and cached and cached, and the normalizer would need to evaluate that. Or we could just open many different connections with different sequence numbers and different spoofed source IP addresses, and then the normalizer would need to cache all the states for all these connections. So that's another form of a DOS attack. Okay, now I come to the detection of covert channels. I will exemplify this using the interpacket times pattern. Just as a short reminder, I discussed the interpacket times pattern in the chapter on patterns. It's the first timing pattern, and it modifies the inter-arrival times of packets to signal hidden information. So, for instance, if you send a packet, if you send succeeding packets either with a delay of 1 or 2 seconds, then it could be a 0 or 1 bit. That would be a simple inter-packet times channel. So there's interesting work of Berk et al. I will fix the typo. And they said that the interpacket gaps of non-covert traffic are distributed in a way that most of the measured interpacket gaps are close to an average IPG value X, while inter-arrival time-based covert channels, that's those created by the interpackets pattern, signal hidden information using at least 2 different inter-arrival time encoded symbols, resulting in at least 2 instead of 1 peak of IPG values. So as you can see in the chart here, in the plot here on the right side, so we have here at the x-axis, at the bottom axis, we have the interpacket gap, the time between 2 succeeding packets. And we have the number of packets that that are sent or received after such a time gap. So for normal traffic, or legitimate traffic, we have usually something like the blue line. I plotted this here on my own. It's not based on real traffic. It's just to reproduce the idea, just to explain the idea. So in real traffic, this might not be such a perfect shape. And the most of the traffic will have some inter-arrival time x. In that case, it's 0.03. By the way, the 0.005s are missing. So this is 0.001, 0.0015, 0.002, 0.0025, and so forth. And for covert channel that uses interpacket gaps, you have at least 2 different symbols that you need to transfer. So either you transfer a 1 bit or 0 bit, and let's say the 1 bit is 0.016 and 0 bit is 0.045 here. So we have 2 peaks here, but few in between for our flow. And in that case, our flow is suspicious. So The procedure to detect such covert channels is as follows. We first record all the interpacket gaps for each flow. Then we calculate the number of packets with an average inter-arrival time value. Sorry for mixing IPG and IIT here, because back a few years ago I always used IIT and I just cannot edit this slide anymore for some reason, I don't know. So IPG and IIT is the same. And we also count the highest number of packets with the same IIT. So for the legitimate traffic, most packets are here at 0.03, and that's also approximately the average value, and most packets are here too, so we divide approximately 1 by 1 here. We subtract this value from 1, so that for normal legitimate traffic we reach a probability for a covert channel that is close to 0, while for the covert channel the average interpacket gap is around here at 0.03 something, but we have very few packets here, while the big number occurs here for 0.016 or something like that. So if we divide these values, then the resulting value will be very small. So 1 minus something small is still close to 1, so the probability for having covert channel is rather high. I like this approach by Berk et al. Very much because it's easy to understand and it's working nicely. Okay, another approach comes from Cabuk et al. And is called Epsilon-Similarity. It works also in an easy way, and it's pretty useful. We used it for our own research also a couple of times. I will discuss this aspect later. So how does it work? We first record all interpacket gaps of a flow, as you can see in the first chart. Then we sort all these interpacket gaps. And next step is we calculate the relative differences, this blue dashes here. And finally, based on these increases, we look how many of them are below a certain threshold epsilon. This is the orange line here. So given that I introduced the Berk et al. Method on the previous slide, you know why this is done and why it works. So for a covert channel, you have usually many packets that have highly similar interpacket gaps. So you have in the most extreme case, you have like a ladder, steps in a ladder here. You have sharp increases. Well, for legitimate traffic, you will have smoother increases. So the relative differences for covert channel traffic will be larger, higher as in case of normal traffic or legitimate traffic, at least for most legitimate scenarios. This is not a perfect approach. And you can then count how many of your lambda values, that's the relative differences, are below the threshold epsilon, and then you have an indicator for the presence of a covert channel. Requirement here is that you always take the same number of packets. That's called a window or window size. For the second scenario by Cabuk et al., which is the compressibility score, we also need to consider a window size. And for this window size of, let's say, 2000 packets, we also record the interpacket times, which I call here delta T1 to delta Tn. In that case, for the window size of 2000, it would be delta T 2000. We then encode the interpacket times in an ASCII string. In the original paper by Cabuk et al., they rounded the values and used a coding like this, where the letter at the beginning of a measurement indicates the zeros behind the comma. So it would be 0, and the remaining value, the remaining numbers would be rounded. So this would be 0.02 something seconds, and again, and 0.19 something, 0.03, 0.029, 0.20, and so forth. And then You select a compressor. In the original paper they used gzip. We also used gzip in our tests. And you compress this ASCII string S, and you get out of this a compressed string. And then you calculate the so-called Kappa value, where you check the compressibility of the string. So you divide the length of the original string by the compressed value. You can also flip these values, then you just get another range. So it doesn't matter how you do it, it just matters that you always do it the same way. And you can also play around with the coding here. It can be done in several different ways. So, and as covert channel traffic always uses very similar inter-arrival times or inter-packet gaps, you get the same value many times, which leads obviously to a higher compressibility than normal traffic. So this is a good way to detect such traffic. Here's an overview of our ACM CSIR paper, the patterns paper, where you can see that several different, that's back 2015, so we extended this already, but in general it's still valid. So with traffic normalization you can combat many channels, either by eliminating or by limiting them. Actually, you can also, as already shown in other research work, perform a traffic normalization against a size modulation pattern, or at least a limitation approach here. But that's not a good approach, because it usually makes packets much larger. And with the statistical and machine learning approaches, you can try to detect them all. Note that this is the original 11 patterns, and that we have more patterns now, as I have shown in the chapter on patterns. Okay, so as you might know, and I already mentioned it, we have 20-something patterns now, and we lack countermeasures for several of the known patterns. And when the table on the previous page has shown that detection should be feasible, it doesn't mean that there is a solution already present for each pattern. And for this reason, we came up with an idea we call countermeasure variation. So I copy and pasted the definition of our paper here. So I will just read it. Given two hiding patterns, A and B, that are different from each other, a countermeasure variation is a pattern-based process in which an existing countermeasure that detects, limits, prevents, or audits covert channels of pattern A is modified so that it detects, limits, prevents, or audits covert channels of pattern B. So that means, for instance, that just to give you an example, that the inter-arrival times pattern by that could be detected using the method by Berk et al. Would then be switched as a context, so that the method by Berk et al. Would be applied to a different pattern, let's say size modulation, and we would try to modify the Berk et al. Method to detect that pattern. The process of countermeasure variation replaces the input attributes, features, used for pattern A with features for pattern B, and performs a modification of the inner functioning used for A in order to work with the new features for B. And the rest is details. You can read it, but I will show you a very brief and simple explanation. So let's look at the above graphic. So a classic covert channel countermeasure looks like this. We get some input data, like inter-arrival time between packets and the packet number. Then there's some detection method. For instance, the calculation of compressibility score by Cabuk et al. And we get some detection results that are hopefully useful, and the quality makes it good enough for our purpose. With countermeasure variation, we take such a existing countermeasure, like the one here. So we still take the one, let's say, from Cabuk et al., so the compressibility score, but we replace the feature of the first pattern, so let's say it's the flow-based inter-arrival times for the inter-packet times pattern, and we replace this with flow sizes to detect the size modulation. And we alternate, we modify, slightly modify as slightly as possible the original algorithm so that hopefully the detection results still are useful for us. And we did this. So we performed such a countermeasure variation using the compressibility score and Epsilon-Similarity, and actually also another metric called regularity metric, but this is off topic for now. And we did this for different patterns like size modulation, artificial retransmissions, sequence modulation, and message ordering. So let's look at a few of them. Let's first look at the message ordering pattern and how we used the compressibility score there. Slight reminder, how does the message ordering pattern work? So in a legitimate transmission, most of the segments of a TCP flow, this works also for other protocols, but TCP is the perfect example to explain it, would be in order. So we send segment 1, 20, 21, 22, 23, and so forth with increasing sequence numbers, while a covert channel's traffic would look different because the manipulated order of the segments would indicate the hidden meaning. So we, for instance, could send first segment 1, 21, 20, 23, 22. And of course, then we have a different sequence number here as well. So I developed the following approach that works as follows. First, we need to record the traffic, for instance, capturing live traffic or using an existing traffic recording. And then we enumerate the packets. So we see that sequence number 10 comes first, then 100 and so forth. And then we can say, okay, this is the first segment, this is the 35th, 36th, 38th, 37th, and so forth. And we write down the negative, the relative differences between these numbers here. I used a window size of 200 differences. That means I had to record 201 packets. This window size just worked well. And then I encode this in a string. So the easiest way would be to just write these numbers behind each other and then the string is done. That didn't perform so well. What performed best was to write down the absolute difference concatenated with the absolute difference modulo 2, and when it's depending on whether it's 1 or 0, I would concatenate an A or an B. So that worked well. So the optimally produced legitimate flow would look like this: 1A, 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 because all TCP segments would be in order, and the string length would be 400 because I have 200 packets and I need 2 symbols, 2 characters per segment, resulting in a maximum compressibility of 14.8 using gzip on the command line, while the compressed string was 27 bytes long. So yeah, as also done by Cabuk et al., I just compressed the string to calculate C and then calculated the kappa value by dividing one value by the other. Here I divided the compressed string length by the original uncompressed string length. And if we look at such values, I used the NZEX legitimate flows to calculate for many packets, few million packets and several thousands of flows, their compressibility scores. And then I also created covert channels that modified either the order of always 2 PDUs in a row or 3 or 4 PDUs. And here you can see the average kappa values. And as you can see, most of the legitimate traffic was found in a range larger than, let's say, 7. But some legitimate flows also look like covert channels, covert channel flows. Not too many, but some. So this is always the challenge if you have a non-trivial detection approach, because you have to deal with these overlappings. If I use the kappa value as a threshold for detection and calculate standard values like precision recall, F-score, and accuracy, then for the PDU, the 2 PDU channel that always changes the order of 2 segments, I get a maximum combined value for accuracy and F-score of 94.5 and 7%, which is around here at 4.2 something. While for the 3 PDU channel, it's much easier. I get higher accuracy and F-score values as seen here. It's both above 99%. This is already a good detectability that is useful for also some scenarios with larger traffic volumes where only few false positives are allowed. If I even use 4 PDUs, then the detectability increases further. So I get an F-score of 99.5 and 99.5 accuracy and F-score. So the more PDUs are flipped in order in a row, the easier it is to detect the channel. The optimal threshold was for 3 and 4 PDU channels was between 2.75 and 3.0 for kappa. This resulted in a false positive rate of between 0.26 and 1.04% approximately, which is pretty nice. So the dashed line here is a 1% false positive rate, while the orange one is a 5% one. And for the 2 PDU channel, it was not so easy. So I got a false positive rate of 5.19%, which is slightly below, above this orange line here. But the 3 and 4 PDU channels were nicely detectable. So I tried to use a decision tree classifier, namely C4.5, to determine finer thresholds for kappa. And here's the result. First of all, with the current approach, and secondly with C4.5, I used the weaker tool to do this. So as you see, the differences are not that big, but if I zoom in, then the optimized threshold that I didn't found by hand because I didn't make it so precise can increase the results still a bit further, especially for the 2 PDU channel. It's more than 1% for the 2 PDUs, and still a little bit increase for the 3 and 4 PDU channel. The false positive rate could also be increased. I zoom in again. So for the 4 PDU channel, I could decrease it using a finer threshold to 0.09%. And for the 3 PDU channel, I could also decrease it, and even for the 2 PDU channel. However, this is a non-pruned tree. So usually you prune trees, and I didn't do this because I wanted to know what's the maximum I could achieve here, and this is why I used C4.5. I still think one should go with not so fine thresholds, because then you get a higher false positive rate, but you are also capable of handling more traffic scenarios nicely. Even if it's not the traffic that I used by the NZ-IX internet exchange. So maybe it looks slightly different for traffic that is from 2020, because the recorded traffic was already quite a few years old. So I would suggest to go with the thresholds that I mentioned earlier, and not the C4.5 ones. But anyway, this is to show you that one can play around with this and get improvements. especially if you apply multiple thresholds. Let's say it's legitimate between Kappa 2.57 and 2.56, but the values surrounding it are not legitimate. And then you are very specific for some specific legitimate traffic, but maybe in another case this is actually covert channel traffic. So let's go to another countermeasure variation. Let's look at the artificial retransmissions pattern and the compressibility score and the Epsilon-Similarity. This is work mostly done by my student, and so the retransmission pattern works as follows. We send some original packet, and then if we retransmit it, it's a different meaning than if we do not retransmit it. And we first studied typical retransmissions of internet traffic over different routes, repeated the measurement several times for each route at different times of the day and hours of the day, and adjusted and optimized the covert channel to legitimate traffic's characteristics. Also, the covert channel has a very low transmission rate to increase the covertness and a robust coding for error detection. So this time we have a sophisticated covert channel that looks like legitimate traffic that also has retransmissions. But could we still detect this with a countermeasure variation? Well, we performed Epsilon-Similarity and compressibility score-based countermeasure variations. And for the Epsilon-Similarity, we had to modify the input in the way that instead of inter-arrival times, we looked at succeeding retransmission sequence numbers and modified the algorithm's thresholds. And for the compressibility score, we looked at succeeding retransmission sequence numbers too and replaced the string coding where in the original approach the inter-arrival times were transferred into some ASCII string coding with a new algorithm that uses a different strategy to deal with the unsigned 32 bits sequence number. Also, the thresholds for detection had to be adjusted as always. And let's look first at the Epsilon-Similarity. So at the left side, you see a recording of covert channel traffic's sequence number deltas. And at the right side, you see legitimate traffic. Of course, this is a covert channel that sends a lot of data. So it's not that we always send such covert channel traffic. We really used covert channel traffic that sent very few retransmissions, but this is for showing how it works. So if we sort these values, then you get the smooth increase for the regular traffic, and you get sharp increases for the covert channel traffic as seen on the left side. Now, if you calculate the lambda values, which are the relative increases here, and apply some threshold, then you will see that for the covert channel traffic, a different number of lambda values are below and above the traffic than for legitimate traffic. If we distribute, if we look at the distribution of the scores for different epsilon thresholds for legitimate and covert channel traffic, then we can already see visibly that there is a clear difference, but you still have to apply some detection thresholds. So if we look at the detectability while applying two thresholds, then we can detect covert channel traffic pretty nicely. So the only covert channel traffic that we couldn't detect is where we had gaps of at least 500 packets between retransmissions. So we had a very low covert channel data transfer rate, and where we overall had very few transmissions, at maximum 27 retransmissions in a flow. So everything else was detectable with the Epsilon-Similarity. So that means the countermeasure variation worked nicely. We also did this for the compressibility score, but as you can see here, kappa values for legitimate and covert channel traffic overlap quite a lot. So please keep in mind this was an optimized channel. A trivial retransmission channel could most likely be detected easily, but that was not the interesting challenge here. So however, such a sophisticated channel was not easy to detect. We had quite a high false positive and false negative rate, so this is not suitable for many scenarios. It can be used as a feature for some machine learning approach that, for instance, combines the compressibility score with the Epsilon-Similarity. Then it could increase potentially the overall detectability of such channels. So the size modulation is something that we worked with using the compressibility score, the Epsilon-Similarity, and a third metric called regularity metric that you find also explained in our paper. But I think for didactic purposes, it's enough here to discuss the first two because I introduced them. So size modulation was simply we encode different packet sizes, secret symbols using different packet sizes. And I don't go into all the details here, how we did it. It's similar like in the previous two approaches. And as you can see here, so we transferred different traffic to test exactly how it works for different kappa values at different interval sizes. We used different thresholds for the detection, and it was nicely feasible with some intervals to detect channels that, for instance, use channel packet sizes of 1000 and 1001 bytes, or that used 50 or 60 bytes. However, as you can see, the intervals were different and they were not so much overlapping and partially not even overlapping at all. And that means it's pretty difficult to detect such channels in a sense that all combinations of packet sizes can be detected. So it's easy to use this interval to detect channels that have 1000 and 1001 and 100 and 101 or 200 and 201 or 257 and 256 bytes in size. So there's just 1 byte difference. But if the difference is 10 bytes, then it's already a different interval. And if it's 100 bytes, then again, intervals shift. So it's not always feasible to perform such a detection. And if we combine all two size covert channel variants that we tested and try to detect a mixture, then as you can see, the accuracy goes down to 60-something%, which is pretty bad. Or here we have at most 71 or 72 with a precision of maybe 82%. And if we use 3 sizes, 100, 200, and 300 bytes, then it's again challenging, but the interval is at least the same as for some two packet size values, namely the interval 7 and 8 and 6 is good here. So we can use this nicely for such channels as well. We also try to transfer channels with differences using 8 packet size values, 100, 200, 300, and so forth, till 800 bytes. And here we can only detect them with the first interval, or interval number 1 actually, because second as interval number 0 is the first. So overall, this leads to the problem that it's not feasible to apply just one threshold. Because if you want to detect all these channels, then you need to apply many thresholds. When we used the Epsilon-Similarity, it worked rather nicely for 2 simple covert channels, but we couldn't detect those with 3 symbols. And we had to use very narrow thresholds. Only then it worked. So overall, the Epsilon-Similarity seems to be a very specific tool here, and both the compressibility score, Epsilon-Similarity, and also the regularity metric should be used in a machine learning based classifier, so that all three metrics are combined to draw conclusions. And then I believe that size modulation patterns can be detected nicely, but that's still to be done. So, some conclusions on countermeasure variation. First of all, it works, but we need to apply thresholds that we first need to study, and we need different thresholds for different situations, like different covert channel configurations, such as packet size, inter-arrival times, and so forth. And also we need to further study other algorithms. How do they work with a countermeasure variation? So that's also difficult. And finally, one needs to apply many thresholds in parallel, which is quite some effort. All right, that's all for chapter 7a. In chapter 7b, we will look at sophisticated countermeasures.